So one of the ways that we can, or several methods that we can use to analyze polymeric material, and especially the structure of polymers, is going to be with XRD and also with DSC analysis, so differential scanning calorimeters. So we've talked about XRD analysis in this course before, but we want to remember that we have n lambda equals 2d. D here for polymers, we're not going to have any HKL indices. It'll just be some characteristic distance that repeats times sine theta. So our distance is inversely proportional to our angle here. So if you look at these plots, these are for different families of methacrylates or methacrylate polymers. So these methacrylate polymers, the only thing that changes is the number of these methyl R groups. So if you look at the structure, we have some distances here, very small distances between our intra-chain distance here and this length here that are not changing. But as we add more methyl groups, this distance will change, and this distance is definitely going to change as well and shift. So we have these large distances, right? Large distances, so if my distance is large, that means my theta is very small, that are changing between, as we go down here, the CH3 groups are actually increasing. So meaning that the distance should be increasing, as we go down this plot. And you see that these peaks are splitting and then shifting. You can see this peak here, here, and here. They're moving to the left. So we can tell in this analysis that these CH3, the number of these CH3 groups are actually increasing because the distance between, for example, the interchain distance is increasing and our theta must decrease. And so you see these peaks shifting to the left. These peaks here, they're not really changing distances at all. Those occur at large theta. So if theta is large, that means our distance must be very small. So those are the distances that are conserved. So XRD analysis isn't just used to tell a semicrystalline versus a semicrystalline versus amorphous polymer, but we could actually get some fairly interesting details in that as well. Now, differential scanning calorimetry is a technique that's used. You have two pans. One is your reference, one has your sample, and you basically are connected here, and you heat up these pans at a specific heating rate. It could be 10 degrees K per minute. And you heat up this, and we measure the differential heat flux, or our delta H. So basically, what's the difference as I go from 25 to 26C? What's the as I increase that temperature, how much heat do I have to supply to here versus here? So that's the delta H, the differential heat flow that I'm measuring. So when we're measuring this, and typically these plots will have endo on the top, and actually here you see, this is actually a mistake. This is exo, and this is endo. So this is endo, and you can see that here my polymer always goes through a glass transition temperature. Every polymer will exhibit this. So this is a semicrystalline polymer. So this is crystalline. And we see that the slope is going up because we're absorbing energy. So endo, so we're absorbing energy in order for those molecules to start to move. You'll see here for this particular crystalline polymer, this doesn't happen for every crystalline polymers, we actually go through this endothermic reaction. That enthalpy of recrystallization, and this temperature is a recrystallization. So as those polymers move around, they actually start to form lamellar structures and recrystallize. So that's an exothermic reaction because they are forming heat. Or actually, they're releasing heat, excuse me. But as we increase temperature again, then we see our characteristic spike, our discontinuity, because this is a first derivative of Gibbs, another discussion, first order phase transition. This is a second order thermodynamic phase transition. And we see this is our enthalpy of fusion. So it's the energy absorbed as we go through melting. Now, if I'm a fully amorphous polymer here, I'm going to go through this glass transition temperature, but that's it. There's no melting because I am not a crystalline material. So that's kind of the key idea here. Now, you can also look at thermoplastics versus thermoset polymers. So thermoset polymers are like epoxies and resins. JB Weld is a great example. Not sponsored, but I would like to have them as a sponsor. So the thermoset polymers, they're going to exhibit the TG, and then they're going to cure. So just like when you mix the resin and you feel that heat that's released, they're chemically cross-linking. So they are forming chemical bonds that will never break. So one of the cool things is that this curve for thermoplastics, you can heat them, melt them, and then cool them, and you'll see an opposite, basically, and then, basically back here. But you can kind of heat and recool them, and they'll retrace. But once we cure the polymer, and we go back, and we heat it up again, it'll go through a TG, but it will never exhibit this cross-linking exothermic reaction again. So that's kind of the unique thing about thermoplastics. We can reuse and we can reheat them and basically form them again, but we can't do that for thermosets. So that is our end of our journey together in material science. I hope you enjoyed the class, and we'll see you next class, next time. Thanks.